Electricity and magnetism are interrelated and are also interconvertible. Let us look at a few examples. In this setup, an electric current passing through a conductor produces a magnetic field, which can be observed through the deflection of a magnetic compass needle placed near the conductor. This proves that moving electric charges produce magnetic fields. Electric motors work on this principle. However, in this setup, we see that an electric current is induced in a closed coil when subjected to a changing magnetic field. The phenomenon in which an electric current is generated by varying magnetic fields is called electromagnetic induction. Electric generators work on this principle. We will now discuss and learn about 3 experiments by Faraday and Henry relating to electromagnetism. In the first experimental setup, a coil is connected to a galvanometer. When a bar magnet with its north pole facing the coil is moved towards or away from the coil, the galvanometer needle deflects to the right and left side of 0 reading respectively, showing the presence of a current in the coil. Now, let us see what happens if the south pole of the magnet faces the coil. The galvanometer needle deflects to the left side of 0 reading as the magnet approaches the coil and deflects to the right when the magnet moves away from the coil, showing the presence of a current in the coil. The galvanometer needle deflects only as long as the bar magnet is in motion. Once the bar magnet comes to rest, the galvanometer needle settles down at 0 reading, indicating that there is no current in the coil. From all these observations, we can conclude that whenever there is relative motion between a bar magnet and a coil, an electric current is induced in the coil. In the second experimental setup, there are 2 coils. Coil 1 connected to a galvanometer, coil 2 connected to a battery. Due to the steady current in coil 2, a steady magnetic field is set up around the coil 2, and this magnetic field is also linked to the coil 1. When coil 2 is kept stationary and coil 1 is moved towards coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the left of 0. When coil 2 is kept stationary and coil 1 is moved away from coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the right of 0. If we keep coil 1 stationary and move coil 2 towards coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the left of 0. Now, if we keep coil 1 stationary and move coil 2 away from coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the right of 0. From all these observations, we can conclude that whenever there is relative motion between a current-carrying coil and a closed coil in which a galvanometer is connected, a current is induced in the closed coil. In the third experiment, a tap key is provided in the coil 2 circuit. Here, we can observe the deflection of the galvanometer needle even when the 2 coils are stationary. This deflection is observed only at those instants when the tap key is either switched on or off. This happens because of the change in magnetic field during switching on and off. When a ferromagnetic material like an iron rod is placed coaxially along the two coils, the effect of the magnetic field linked to the coil 2 increases due to the nature of the ferromagnetic material, as it allows more number of magnetic lines of force to link within the area of the coil. Hence, the deflection of the galvanometer needle increases, indicating an increase in the induced current. Before attempting to understand Faraday's law of electromagnetic induction, we should recapitulate the terms used in electromagnetic induction. These terms are representation of a surface area by a vector A, uniform magnetic field B, and magnetic flux phi B. The area of a plane surface is represented by a vector A drawn along the outward normal to the plane surface. In the case of a curved surface, the surface area is split into very small areas, and each is approximated to a planar area. In a uniform magnetic field B, the number of magnetic field lines cutting across an area placed perpendicular to the field lines is same for each unit area of the surface. If a plane of area A is placed in a uniform magnetic field B with its area vector A, making an angle theta with the magnetic field, then the magnetic flux phi B through the area can be written as phi B is equal to B dot A, which is equal to BA cos theta. Let this be equation 1. Magnetic flux phi B can be varied by changing any one or more of the terms B, A, and theta. The SI unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux phi B is a scalar quantity. When the magnetic field has different magnitudes and directions at the various parts of a curved surface, the magnetic flux through the curved surface is computed by extending equation 1. Phi B is equal to B1 dot dA1 plus B2 dot dA2 plus and so on, which is equal to sigma all Bi dot dAi. Let this be equation 2. So far, we have recapitulated the terms used in electromagnetic induction. Let us now learn about Faraday's experiments where we use these terms. Faraday conducted 3 experiments, from which he concluded that an EMF is induced in a coil when the magnetic flux cutting across the coil changes with time. In the first experiment, Faraday observed that the relative motion between a magnet and a coil changes the magnetic flux across the coil. This change in magnetic flux with time induces an EMF in the coil. Similarly, in the second experiment, he observed that the relative motion between the two coils, one carrying a current, changes the magnetic flux across the coils. This change in the magnetic flux with time induces an EMF in the other coil. In his third experiment with 2 coils, he found that if the tap key is pressed, the current in coil 2 and the resulting magnetic field rises from 0 to maximum value in a short time. This results in a change in the magnetic flux with time across coil 1, inducing an EMF in it. If the key is kept pressed, there is a steady magnetic field across coil 1. Thereby, there is no EMF induced in it and the current drops to 0. When the tap key is released, the current in coil 2 decreases from a maximum value to 0 in a short time, resulting in the magnetic flux across coil 1 to drop suddenly, thereby inducing an EMF in it. From the observations of these 3 experiments, Faraday concluded that the time rate of change of magnetic flux through a closed coil induces an EMF through it, and stated the Faraday's law of electromagnetic induction. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the coil. We can put this law in the form of a mathematical equation: E is equal to minus d phi b divided by dt. Let this be equation 3. In this equation, E is the induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. When n number of turns are closely wound to form the coil, the change of flux with time for each coil is the same, and we can write for the total induced EMF as E is equal to minus n into d phi b divided by dt. Let this be equation 4. In this equation, E is the total induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. Therefore, the total induced EMF can be increased by increasing the number of turns n of the coil. Before attempting to learn about Lenz's law, let us first recapitulate about the right-hand grip rule applied to a current-carrying coil. Consider a right-hand fist with the thumb extending out. If the fingers are wrapped in a circle pointing in the direction of the current through the coil, then the thumb points towards the end of the coil, indicating the north pole. Lenz's law helps us in identifying the polarity of the induced EMF in a coil. Lenz's law states that the polarity of induced EMF in a closed loop is such that it tends to produce a current which opposes the change in the magnetic flux that produces it. We can put this statement in simple terms. If a current is induced by an increasing flux, it will weaken the original flux. If a current is induced by a decreasing flux, it will strengthen the original flux. The magnitude of the induced EMF is given by Faraday's law, which is E is equal to minus d phi b divided by dt, where E is the induced EMF in the coil and phi b is